A 5-kilogram block sits on a ramp that is at an angle of 35 degrees with the ground. The block is initially 1.0 meters above the ground, and the coefficient of kinetic friction between the block and the ramp is 0.45. What is the velocity of the block when it reaches the bottom of the ramp? We will draw a picture of the situation, labeling the angle of the ramp to the ground theta, the initial height of the block h, and the final velocity, which we expect to be parallel to the surface of the ramp. Now we will list our knowns and unknowns. The mass of the block is 5.0 kilograms. The angle of the ramp to the ground is 35 degrees. The initial height of the block is 1.0 meters. The initial velocity of the block is 0,0 meters per second. The initial position of the block can be labeled 0,0 meters, and the final position of the block can then be found as h over tan theta, negative h meters. Lastly, the coefficient of kinetic friction between the block and the ramp is 0.45. Our unknown quantity is the final velocity of the block. This time, we will solve this problem using the energy principle, which states that the change in energy of the system is equal to work plus heat exchanged. In this case, we will assume that no heat is exchanged with the surroundings. The change in energy of the system can be split into kinetic and potential energy, leaving us with the final expression we will use, delta Ke plus delta U equals W. Now we will find V final. The change in kinetic energy is just the final kinetic energy minus the initial kinetic energy, where each is given by 1/2 mv squared. In this case, V initial is 0, thus the initial kinetic energy is also 0. This means that the change in kinetic energy is equal to 1/2 mv final squared. The change in the potential energy is given by the final potential energy minus the initial potential energy, or mgy final minus mgy initial. Since the block goes down a height h and loses potential energy, we know that delta U is equal to negative mgh. Next, we will find work. Work is given by the force dotted with the distance over which it acts. The dot product of these two vectors is a scalar. In our case, the force is the force of friction, and the distance over which it acts is the difference between the block's final position and its initial position. Now we will find the force of friction. We know that the magnitude of the force of friction is given by mu k times the normal force, and the direction of the frictional force is parallel to the surface of the ramp. Since the friction force opposes the motion of the block, we know that its unit vector will be given by negative cosine theta in the x direction and sine theta in the y. Now we must find the normal force. Sketching a quick free body diagram, the force of friction, the normal force, and the force of gravity. We know that there is no motion perpendicular to the surface of the ramp, and therefore that the normal force is equal to the force of gravity times cosine theta. Thus, Fn equals mg cos theta. The force of friction is given by mu k mg cos theta times the vector negative cos theta in the x direction, sine theta in the y direction. Work is then given by mu k mg cos theta times negative cos theta, sine theta, dotted with h over tan theta, negative h. When taking the dot product of two vectors, you sum their component-wise products. In this case, fx times rx plus fy times ry. This gives us that work is equal to mu k mg cos theta times the quantity negative h cos theta over tan theta minus h sine theta. Factoring out a negative h and distributing the cos theta, we have negative mu k mgh times the quantity cos theta cubed over sine theta plus sine theta cos theta. Now we will plug these results into our energy principle expression and solve for V final. Plugging in our results for delta Ke, delta U, and W. Plugging in our results for the change in kinetic energy, the change in potential energy, and work, we have 1/2 mv final squared minus mgh equals negative mu k mgh times the quantity cosine cubed theta over sine theta plus sine theta cos theta. We can bring mgh over to the other side and then multiply both sides by 2 over m to isolate v final squared. We can then take the square root of both sides, giving us our expression for v final as the square root of 2 over m times the quantity negative mu k mgh times the quantity cosine cubed theta over sine theta plus sine theta cos theta plus mgh. Plugging in our numerical values and evaluating, we find that the magnitude of the final velocity of the block is 2.65 meters per second. We can find the x and y components of this velocity using trigonometry. We know that the velocity is parallel to the ramp and that the angle between the ramp and the horizontal is theta. Thus, Vfx is given by Vf cos theta and Vfy by Vf sine theta. We find that the final velocity of the block is 2.17 meters per second in the x direction and negative 1.52 meters per second in the y direction. Now we will perform our sanity checks. First, we will check the units of our result. We have that the square root of 1 over kilograms times the quantity kilograms times meters per second squared times meters plus kilograms times meters per second squared times meters is equal to the square root of 1 over kilograms times kilograms meters squared per second squared, which is equal to square root of meters squared per second squared, which gives us meters per second as we desire. The order of magnitude of our result is reasonable for the situation. And for our final check, we can see that this result matches our result from when we solved this problem using the momentum principle.